Let me take a look at logarithmic functions with you. This is section 4.3 out of your book. Now, with logarithmic functions, the main thing that we're going to be talking about with them is how they are the inverse of exponential functions. So let's kind of recall some of the ideas that we've had with inverse functions in the past. So first, we've had power inverses. So if I have something like x raised to the third power, or x cubed, something like if I plug a 5 into that, well, we know 5 to the third power, or 5 cubed, is 125. So you're inputting 5 and you're outputting 125. Its inverse has to undo that relationship. So you need to be able to plug 125 in and get a 5 out. Well, notice I'm saying the inverse of that function is the cube root, because I can plug 125 into the cube root of x, and I would get back out a 5. The cube root of 25 is 5. It undoes the original relationship. Similarly, if you just have multiplication and division, obviously they're inverses of one another. If I have something like 4 times x, I'm inputting a 10, and I get out a 40. 4 times 10 is 40. Well, the inverse of that multiplication is division, so the inverse function would be x over 4. Well, you could input the 40 into that. 40 divided by 4 gives me back the 10. Inverse functions. Now, some other inverse functions that we definitely need to be keeping in mind now are the inverse functions of logarithms and exponentials. Now, notice up here I called this a power versus an exponential. Because power functions, or polynomial functions, are when we have a variable base and a constant exponent. Now, if you have an exponential functions, then you're going to have a constant base and a variable exponent. Something like the exponential function 3 raised to the x power. Well, what if I said I want you to plug an x value of 4 into that function? You can say, okay, well, that's 3 to the 4th. 3 to the 4th means 3 times 3 times 3 times 3. 3 times 3 is 9, times 3 is 27, times the fourth 3 is 81. So I can say, well, 3 to the 4th power is 81. The inverse of that, though, would be the log base 3 of x. Whenever I say the log base 3 of 81, I am literally asking you, hey, what power of 3 do I need to get an 81? It's undoing this function where the answer is what I inputted over here. Well, the log base 3 of 81 is 4. Now, whenever we have exponential expressions, you can say, well, over here, if the answer is x, and I say x is the answer to the exponential function a to the y, the equivalent logarithmic form would be to say, well, the answer becomes the domain over here, and I'm going to say the log of a to the log base a of x is equal to y. So this is telling you a to the y power is equal to x. That's what this over here, a to the y power is equal to x. These two mean the exact same thing. Now, knowing how to rewrite from logarithms to exponentials and exponentials to logarithms, extremely important. And we're going to be talking about that a lot more throughout this section as well, particularly when we solve out equations and stuff. Let's go ahead and look at a few logarithmic forms here on the next page. I'm wanting you to evaluate these logarithms by rewriting them in their equivalent exponential form. So if I have something like the log base a of x, you literally need to ask yourself, what exponent or power do I need to raise that base a to get the term in the inside, which is x in this case? So if I give you something like log base 4 of 64, notice I wrote down here how you read that equation or that expression, log base 4 of 64. Well, what is the log base 4 of 64? It is literally asking you, what power do I need to raise 4 to get to 64? Well, I know 4 times 4 is 16. 16 times 4 is 64. I could multiply 4 by itself 3 times and get a 64. That's why I said, well, this question mark over here is 3. What is the log base 4 of 64? It's 3, because 4 to the third power is going to be 64. Now, notice you do have a log base on your calculator as well. I'll show you that here. It's going to be math, and then it's A, So if I say log base 4 of 64, you get your 3 that we talked about. But that's merely because 4 to the third power is 64. It's asking you, what number would you have to raise the base of that log to get the number on the inside of the log? Now, this next one should be very easy. You say, well, the log base 5 of 5. It's literally asking you, hey, what power do you have to raise 5 to get 5? And you know 5 to the first power is 5. So in this case, our log base 5 of 5 is simply 1. This one's a little bit more complicated. The log base 7 of 1 over 49. So this is asking you, what power do you need to raise 7 to get 1/49th? Well, in order to see that a little bit better, I knew that 49 was 7 squared. So I wrote this as the log base 7 of 1 over 7 squared. And then I said 1 over 7 squared could be rewritten as 7 to the negative 2. Now it becomes more obvious. The log base 7 of 1 over 49 is the log base 7 of 7 to the negative 2. This is literally asking you, what power of 7 would you need to raise it to get 7 to the negative 2? Obviously, it's the negative 2 power. Now, if you wanted to check that with your calculator, you could. You could say math log base 7 of 1 over 49. And please notice, it'll give me that answer of negative 2. Now, log base 3 of 1. Well, you're supposed to remember any number to the 0 power is 1. So I could rewrite that 1 on the inside as 3 to the 0 power. And then it's literally asking you, what power of 3 is 3 to the 0 power? And then you say, well, the power of 3, that's 3. Clearly, it's 0. Your answer to this is 0. Now, on a side note, every single solitary time you have 1 inside of a logarithm, the answer is always 0. Any number to the 0 power is 1. So the log base any number of 1 is always 0. If you tried this one on here, log base 3 of 1, please notice, you get the 0. Now, the last one here, the log of 100,000. So this is asking you, and anytime you don't see a number, it's not a typo. So anytime there's not a number written, it's understood to be what's called the common log. Since our number system is a base 10 number system, we have tens, hundreds, thousands, 10,000s, and so forth. The understood base of any logarithm is always base 10. Now, this is literally asking you, what power would I need to raise that understood base of 10 to until I get to 100,000? And we know that, and it's really as simple as counting the number of zeros. There's 5 of them. But you could say 10 to the first power is 10. 10 to the second power is 100. 10 to the third power is 1,000. 10 to the fourth power would be 10,000. 10 to the fifth power is 100,000. So you could count it out like that as well. Of course, you could also go to your calculator. You don't even need the math button here. You have the log common log just right on the calculator. And you could say in this case the common log of 100,000. And you get it like that. Now, of course, if you wanted to explicitly always just use that log base because it kind of looks cool, you could. Remember, the log automatically means base 10 whether you see it or not. So clearly this will be the same answer there. Now, the other logarithm that we see even more commonly than the common log is the natural log. Natural log is usually just written as ln, but it means log base e. So anytime you see this would be read as the natural log of x, it literally means log base e of x. What number do I have to raise e to get to x on the inside? To look at a couple of these also on our calculator like I was doing above, these don't come out as nicely. Most of the time when you have logarithms, they are irrational answers. If I gave you something like log base 10 of 21,750, now you should already know that the number is slightly greater than 4 but less than 5, because we know that 10 to the fourth power is 10,000, 10 to the fifth power is 100,000. So this is asking me what power would I need to raise 10 to get to 21,750. It has to be a number between 4 and 5. And checking that with your calculator, you just say the log of 21,750 and boom, we get it. Now, I rounded to 5 decimal places there to the 33746. The next one, I'm asking to round to 5 decimal places, and I give you the natural log of 496. So we say, well, okay, this is asking me what number would I have to raise the base e to in order to get 496. Well, I should be able to do that. It's the natural log. And I can say that's the answer. The natural log of 496. And I can do it like that. Now, let's see, could I also do the log base? You have e as a button on your calculator. It's right here. Log base e of 496 should be the same answer. And it is. This is just me trying to show you, okay, yeah, that natural log, it's nothing more than log base e. That's telling us that we would have to raise e to the 6.20657 power in order to get 496. Notice if I wanted to check that, you have the exponential function on there too, e to the x. If I want to raise e to that answer I just got, I'll hit second negative to pull up that answer. This is guaranteed to be 496. If it's not 496, we won't have to do this section. But glorious, it is. So you're thinking, okay, that's kind of cool. Let's talk about the graphs of exponential functions and how they affect logarithms. So what we've been discussing in this, that logarithms are merely the inverse of exponential functions. Now, the fact that they're inverses just means that the x and y values get switched whenever we're graphing them. So I want to go back and remind you how we graphed the exponential function y equals 2 to the x power. We said, well, okay, every single exponential function in existence passes through the point 0, 1, because any number to the 0 power is 1. So we always have that y-intercept at 0, 1. And then I can say, well, what about when x is 1? When x is 1, this is 2 to the first. I have the ordered pair 1, 2 here. What about when x is 2? I have the ordered pair 2, 4 here, because 2 to the second power is 4. What about when x is 3? When x is 3, the y value is going to be 2 to the third. It's going to be 8. And so you see all exponential functions rise really quickly as x goes off towards infinity. The y values go off towards infinity more quickly. And we know exponential functions asymptotically approach the x-axis off to the left. You could plug in a -1 and get 1/2. At -2, it would be 1/4. At -3, 1/8, and so forth. It's getting ever and ever closer. So we say the domain, it moves all the way to the left, all the way to the right, -infinity to infinity. The range, you're only approaching a y value of 0 and you go up to infinity. The y-intercept, I said every single exponential function that's not been shifted, that is, passes through the point 0, 1. And clearly we can see it as a horizontal asymptote of the x-axis, otherwise called y equals 0. Now, the corresponding logarithmic function. Please, please, please remember, all you're doing is you're flipping these x and y values. So this original point that I said every single exponential function passes through the point 0, 1, well, every single logarithmic function passes through the point 1, 0. They have to. And this needs to make sense to you too, because if this x value is 1 here, we can say, well, 2 to the 0 power is 1, so the answer there, the y value would be 0 when x is 1. Well, what about when x is 2? When x is 2, the log base 2 of 2, that's literally asking you what number would you have to raise 2 to get a 2? And you say, well, it's the first power of 2. That's why your answer here is 1. So again, please notice how these points are just the inverse, the flipping of the x and the y. Over here I had the ordered pair 2, 1. I had the ordered pair, I had the ordered pair 1, 2. Let me get them right. When x is 1, y is 2. When x is 2, y is 4. And when x is 3, y is 8. So all three of those points has to be points on our inverse function over here. So we can say, well, the inverse of the point 1, 2 has to be the point 2, 1. It is. That's what I was just talking about. If you put an x value of 2 in there, you can see the answer would be 1 because 2 to the first power is going to give you the 2. The next value, it's going to be the inverse of this. You'll have the ordered pair 4, 2, write it above the curve here. And then that makes sense because if x is 4, you'd say, well, the log base 2 of 4, that's asking you what power of 2 do you need to rise it to get a 4, and it's the second power of 2. And then finally, on up here, it'll be the inverse of the 0.38. It's the 0.83. And so you can see instead of this function going up quickly, this function rises slowly. And instead of this function asymptotically approaching the x-axis, this function is going to asymptotically approach the y-axis. So when we start talking about domain and range, just like I was talking about up here, the domain of the exponential function becomes the range of the logarithmic function. Logarithms go all the way down, all the way up. They have an infinite range. Their domain, though, is limited because the domain of the logarithmic function is formed from the range of the exponential function. So I can say the domain of any logarithm starts at 0. It cannot include 0 and goes off towards infinity. That's why it's going to have that vertical asymptote on the y-axis. And the x-intercept, the y-intercept that we originally had on our exponential function becomes the x-intercept. Every single logarithmic function will pass through that x-intercept of 1, 0 unless it's being horizontally shifted, which we'll see here in a few minutes. The vertical asymptote is going to be your y-axis, otherwise known as x equals 0. Now, down here I've graphed another another logarithmic function, and this one should be pretty easy, pretty obvious. If I ask you to graph any logarithmic function, we instantly know every single logarithmic function that's not been horizontally shifted is going to pass through the point 1, 0. So this is just a standard log base 3 of x. So now you should be able to get these 2 points I did here very easily. And when you think about that, well, where do those points come from? The first x value I wanted to be able to determine what x value do I need before I get to a y value of 1. Well, I know that the inside would have to be 3 because the log base 3 of 3, that is literally asking you, hey, what power do you need to raise 3 to get a 3? And you know it's the 1. So I had to go to an x value of 3 before the y value was 1. And then I thought, well, what x value do I need to have in there before I get to a y value of 2? And then I was thinking, well, that would have to be x equals 9 because this is asking you 3 to what power is 9? You know 3 to the second power is 9. This answer is 2. That's where this point comes from. The x value would have to be 9 before the y value, which is the answer for that logarithmic expression, would equal 2. I plotted in that point, graphed in my curve, and then I remembered all logarithmic functions asymptotically approach the y-axis there. So then I had my domain and range, same thing as above. Intercept, same thing as above. Y-intercept, same thing as above. You can never have a y-intercept unless, again, it's being shifted. Asymptote equation, x equals 0. Now, I keep on talking about unless it's being shifted. Let's look at an example of that. So here I have the log base 3 again, but now it's a negative log base 3, and it's of x plus 2. So what you're supposed to remember, anytime you see a number in with the x, that is a horizontal shift, and it's always in the opposite direction of what the sign might imply. So automatically I know that this logarithmic function, it's been shifted left 2, and that negative out in front is going to reflect it about the x-axis. Remember, if the negative is only on the x, it reflects it about the y-axis. If the negative is out in front of the function, it's going to reflect it about the x-axis. So just to remind you, back on the previous page, we graphed out the base function for the log base 3 of x. So I had this function in mind when I was graphing this function. So I just said, okay, I know that what's going to happen is that I'm going to reflect this function about the y-axis. So it's going to go up super quickly, down slowly. and this point's going to be shifted 2 points to the left. Not only that, but the vertical asymptote that was on the y-axis now has to be shown because it's being shifted 2 units to the left. This asymptote equation, and I didn't put it down here, so I'll write it now. It's the vertical line x equals -2. So that's probably the best first thing to graph out. And then you would say, okay, in standard form, every single logarithmic function passes through 1, 0. This is shifted 2 units to the left, so it's going to pass through -1, 0. And then instead of going up slowly and down quickly, it's going to go up quickly towards the asymptote. It had to be the opposite of this behavior, and then down slowly. Instead of just saying down slowly, I went ahead and figured out what happened to this point. I knew that this point was shifted left 2 and then reflected about the x-axis. So the point 9, 2 became the point 7, -2. That allowed me to graph in my logarithmic function nicely without worrying about how far I was going down or anything. As long as you graph out 2 points on it, you should be fine. Now, the domain of all logarithmic functions, just as we've been talking about, goes from the vertical asymptote. In this case, it was shifted 2 to the left, so the x values could go all the way back to -2, and and then the largest the x values can get is all the way to positive infinity. Now the y values, as always, they'll go from negative to positive infinity. Every single logarithmic function is going to have an infinite domain from negative to positive infinity. They will always have the domain restricted. Excuse me. The intercept here, your original x-intercept and the base function would be 1, 0. As we saw, this one was shifted 2 to the left, so it's -1, 0. And it would also have a y-intercept. I'm not that interested in the y-intercept in this one, so you could set it equal to 0 and solve for x, but I don't really particularly care about the y-intercept here. Typically they don't have a y-intercept. This one only does because it was shifted to the left. Now this other one, I did a different transformation. The previous one, I did a reflection and a horizontal shift. This time I just did a vertical shift. So you say, well, this is going to look much more like our base function. It's just the base function with everything shifted up 2 units. So the ordered pair 1, 0 became the ordered pair 1, 2. The ordered pair 9, 2 became the ordered pair 9, 4. And then you can say, well, again, I'm going to have a domain starting at 0 going to infinity, have a range from -infinity to infinity, as you always do. The x-intercept here, I was interested in finding it, and it took some figuring out to do. So notice over here I said, for the x-intercept, I need to find out where it's crossing there. Typically, x-intercepts are important to find. They're solutions to our equation. So I just said, well, I'll have to set that equation equal to a y value of 0. And when I did that, I got the log base 3 of x is equal to -2, moving the 2 over to the right-hand side. Now, this next step, extremely important here. How did I get rid of the log base 3? Well, I took the exponent base 3 of each side. Exponential base 3 and log base 3 are inverse functions. So what you're not seeing there in my work, and I'll show it down here, I said 3 raised to the log base 3 of x is equal to, I had to raise the other side into the exponent of a 3. This is called exponentiation. Now, this 3 log base 3 canceled out on the left-hand side, which is why I just have an x. And then I had 3 raised to the -2 on the right, which I can then say, well, that's 1 over 3 to the +2, which is just 1/9. That allowed me to see that my x-intercept for this problem was at x equals 1/9, and of course the y value of 0. Y-intercept, there is none. And the reason there is no y-intercept is because the y-axis serves as your asymptote. In terms of x, we could call that x equals 0. Now, cancellation properties, and this is what I used in order to find the x-intercept in this equation. Kind of introduce it down here. Anytime we have inverse functions, you know that when you have one inside of another, they cancel. So I showed you this just to let you see we've been doing this all along. If you have a cube root, how do you get rid of it? You cube it. If you have something multiplied by 2, how do you get rid of it? You divide by 2. Those are inverse functions. In the same way, exponentials and logarithms are inverse functions. So what if I have an exponential base a? How do I get rid of an exponential base a? I take the log base a of that exponential base a, and as I like to say, the a's go aways, and you just have the x left over there. So if you have an exponential base a, all you have to do is take the log base a, it goes away. What if you have the log base a inside of an equation, and this is kind of like I had in this problem here. I had the log base 3 that I needed to get rid of. So what did I do? I put that entire side into the exponent of a 3. But I had to do the same thing to the other side of the equation too. I had to put the negative 2 into an exponent of a 3. If I have the log base a, you're going to have to put that entire log base a expression into the exponent of an a. If you can do that, then the log base a, exponential base a go away, and you're just left with the x. Now, looking down here at some applications or some problems that will apply that thought process. If I say, hey guys, simplify for me the log base 8 of 8 to the negative 2/3. Hopefully you're thinking log base, exponential base, log base 8, exponential base 8. I can cancel those two. They eliminate, as I would like to say, and you just get the negative 2/3. You could also just use the logic and say, well, all this is asking me is what power of 8 is 8 to the negative 2/3 power. Obviously, it's the negative 2/3 power. Or you can also think of log base 8, exponential base 8, eliminate, and you get the negative 2/3 that way. Now the next one, remember, that's our common log, so there's an understood base 10 there. So this is asking log base 10 of 0.0001. So I know in terms of decimals, anytime I have terms to the left of the decimal, this is my tenths position. So this is tenths, hundredths, thousandths, 10,000ths. This is 1/10,000th as a decimal. I went ahead and wrote it as 1/10,000th. The reason I did that is now it's more easy to see that 10,000 is nothing more than 10 to the 4th power. 1, 2, 3, 4 zeros. So 1 over 10 to the 4th power as a fraction is the same thing as 0.0001. Well, 1 over 10 to the 4th is the same thing as 10 to the negative 4th power. Now you would say log base 10, exponential base 10, cancel, and you're left with a negative 4. You could also think of it as 10 raised to what power is 10 to the negative 4th power, and obviously your answer is negative 4 that way. My next one, and this is where you really need to be careful about the cancellations. I was saying up here, anytime you have an a inside of a log base a, those cancel out. If you have an e inside of a natural log base or log base e, exponential base e cancel, and you would have the x. Same thing here. E raised to the natural log, those should cancel out and just leave you with the x. A lot of people would mistakenly just go ahead and, hey, and I have a natural log and e, those cancel out. Well, only if they're immediately beside each other. These are not. In between the natural log and this exponential base e, you have that square root function. So I have to think about the square root, all it means is the 1/2 power. So I went ahead and rewrote this as the natural log of the group e raised to the 2000 pi, and then instead of inside of a square root, I said 1/2 power. Now the reason that this helps is because using the square root as the 1/2 power allows me to see anytime I have power to power, I'm supposed to simply multiply those. So 2000 pi times 1/2 gave me 1000 pi. Now there's nothing between the natural log and the e. I was able to get rid of that square root. The natural log and e cancel each other out. They're inverse functions. You're left with 1000 pi as your answer. Gorgeous. For the next one here, e raised to the natural log of 1234. 1,234. In that case, the e and the natural log are right beside each other. They do cancel out. The next one, more fun, because you see 6 and a log 6. Instantly, a lot of people would just want to say, hey, those two cancel. Well, don't you have 2 times 70? No, 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 no. They can't cancel unless they're immediately beside one another, like the e and the natural log was in the last problem. So what I had to do here was use principles of logarithms that says anytime you have a coefficient out in front of a logarithm, it can be brought up as an exponent on the term inside the logarithm. So I said 6 raised to the 2 log base 6 of 70 is the same thing as 6 raised to the log base 6 of 70 raised to the second power. And then 6 and log 6 can cancel out, and you can say, well, this is just the same thing as 70 to the second power, and 70 to the second power is your 4,900. Now, notice you could have done this on the calculator. It kind of takes the fun out of it, but you could have. I could have said 6 raised to, and then I'll say it's the 2, and then math, log base 6 of 70, better be 4,900. Gorgeous! Okay, guys, wanted to show you this section about working with logarithms. Now in the next section we'll be talking more about laws of logarithms and then solving out equations with them. It's gorgeous stuff.